Hey everyone, Morgan here. So we're going to take a look at some math problems that we alluded to in the lecture. And they're going to be based upon the Clausius-Clapeyron equation, which is page 11 of the Liquids and Solids lecture. Now, I do need to clarify that the AP exam itself would not ask any questions about this, but it does pop up in any other chemistry class. It pops up on the Chem Olympiad. Okay, so I kind of feel like it's important to teach everything in the subject and not just what's on the list for AP Chem itself. Now, the Clausius-Clapeyron equation is that the natural logarithm of P1 over P2 will be equal to the enthalpy of vaporization divided by R times the entire thing 1 over T2 minus 1 over T1, where these temperatures are in Kelvin. Now, this was based upon this graph, where we were able to generate a graph when we put the ln of the vapor pressure versus 1 over T, and we got a straight line going down. And it turned out that the slope of that line was equal to negative delta H naught vaporization over R. And the reason R is there is just some unit conversion. So when you turn this into a two-point form, this is what we end up getting. Now R, because we want this to be in kilojoules or joules, is going to be 8.31 joules per mole K instead of the 0.0821 liter atmosphere per mole K that we used back in gases. Now we can also do it as 8.31 times 10 to the negative third kilojoules per mole Kelvin also. And both of those work fine. Okay, so now we're going to use a couple of these vapor pressures to actually determine the heat of vaporization for water. So the vapor pressure of water at 10 degrees Celsius is 9.209 torr. We'll call that the first set of data, and then the vapor pressure 60 degrees is 1.9 torr. We'll call that the second set, okay? And we'll find the heat of vaporization. So the ln of P1 over P2 equals delta H naught over R times 1 over T2 minus 1 over T1. Isolating delta H, which is what we're interested in, we get the ln of P1 over P2 times R divided by 1 over T2 minus 1 over T1. Now, that means we're going to have the natural log of 9.209 over 149.4. Now, these are both in torr. And when I divide, what's going to happen is torr is going to cancel. Put that in parentheses. Now here I'm going to have my 8.31 joules over mole Kelvin. Then down here, 1 over, now T2 is 333 Kelvin, minus 1 over 283 Kelvin. Now that Kelvin cancels that. So I'm going to have something that comes out in joules per mole. And when I do this, it is 43642 joules per mole K, which is a pretty big number. So it's more likely that this would be 43.6 kilojoules per mole K. All right? Now, this may not exactly match up with what we have in a table in the textbook, but it does match up with the numbers from this question. Okay? All right, so it's a good equation for doing something like that. Now, what else can we use it for? Well, in this next question, find the vapor pressure of water at 50 degrees Celsius, knowing the heat of vaporization is 40.7 kilojoules per mole, and using other common knowledge. Wow. Well, how about that the boiling point of water is 100.0 degrees Celsius, and the vapor pressure at the boiling point is 760 torr. We'll call this state number 2, so this must be state number 1. So when I do my ln of P1 over P2 equals delta H naught over R times 1 over T2 minus 1 over T1. Now I can use the property of logarithms to say that the ln of P1 minus the ln of P2 is equal to that term. All right, and then that equals delta H naught over R, 1 over T2 minus 1 over T1. And to put it into a useful form for me, the ln of P1 equals delta H naught over R times 1 over T2 minus 1 over T1 plus the ln of P2. Okay, equals. Now, I'm going to say 40.7 kilojoules per mole. Then for R, which is downstairs, 8.31 kilojoules per mole K times 1 over, let's see, 100 degrees, so that's going to be 373 Kelvin, minus 1 over 323 Kelvin, plus the ln of P2, which is 760. And I don't need to put the unit because taking the logarithm of a unit, it doesn't make any sense. So the kilojoules cancel, the moles cancel, and this Kelvin will be canceled by those Kelvins. So I'm now into something with no units, which is actually appropriate at this point, okay? So I have the ln of P1 equals, and when I've run all of that through my calculator, I get 4.60. So to get P1, it equals e to the 4.60, which equals 99.6. And we were doing those pressures in torrs. Okay? Now there are going to be other problems like this dealing with equilibrium constants and rate constants in kinetics, so we should get comfortable with this type of problem. Okay. Now one more. The atmospheric pressure on the summit of Mount Everest is 240 torr. What is the boiling point of water at this elevation if the heat of vaporization is 40.7? And again, I'm going to need to know that water boils at 100.0 degrees Celsius, and that vapor pressure is 760 torr. Okay? So this time I think we'll call this set number 1, and we'll call that set number 2. So what am I looking for? I'm looking for a temperature, okay? T2. T2 is my goal. So the algebra is a little more complicated. The ln of P1 over P2 equals delta H naught over R times 1 over T2 minus 1 over T1. Okay? So then I can say the ln of P1 over P2 divided by delta H naught over R equals 1 over T2 minus 1 over T1. Okay? So I can, at this point, actually solve for that. All right? I'm going to have the ln of 760 torr over 240 torr times 8.31 times 10 to the negative third kilojoules per mole K over R, over delta H naught, which is 40.7 kilojoules per mole K. So the kilojoules per mole K are canceling. Okay. Equals 1 over T2 minus 1 over 373 Kelvin. And that's great because I'm in 1 over Kelvin. It's going to work out. Okay. So 1 over T2 in this case equaled 0.002916. Okay. And then T2, when I take the reciprocal of that, equals 342 Kelvin. Okay? And if I wanted to, I could even convert that into degrees Celsius. Okay? All right. So I think that's pretty much what we need to say about these. Okay? Go through them. They are a little bit more algebra than you're used to. Not going to deny that. All right. Hope you're having a good day. This is Morgan signing off.